what am I going to have for number 1?
0.
12.
Yeah, 12. Oh,
Yeah,
no.
it can be 12. If you're, I have someone saying their screen is frozen. Yeah, everyone else can see the PowerPoints, right?
Yes.
Yeah.
Yeah, in that case, I would say try refreshing your screen. Sounds like your browser's stuck. Because it's not Zoom. It sounds like it's your browser.
Or the internet's bad.
What's it? Yeah, like
The
I
internet,
said. Or
the
the
internet
internet,
could be bad.
right, or you lost your feed. Okay, so first one is 12. What's the second one?
0,
0.
0. Third one?
0,
0.
Fourth one?
12,
12.
12. All right. Fifth one?
12.
0.
0.
0, right? Because they're electrically the same between here and here because the switch is open. We dropped all of our voltage across our open switch, so that would have to be 0. What's the next one?
0 also.
0.
0, electrically the same in this one.
0.
0.
0, electrically the same. So let's close the switch now. And let's look at if it changes anything. So number 1, 12.
12.
Okay, number 2,
0,
0.
0, because this is 12 volts and that's 12 volts. They're electrically the same. The meter's going to show 0. How about number 3?
0,
Number 4?
0.
0.
0. Number 5?
0.
Okay, how about number 6?
0.
12.
12.
No, 12 volts.
Yeah,
12
12.
volts,
Yeah,
right?
12
It's my
volts, right.
only load in a series circuit. It has to use all my voltage. So what's number 7?
12. 0.
0.
0.
0, right. So we can see here, unless I'm going across my load. So I went across my load here and I went across my load here. That's why I got 12 volts. Nothing else is going across the load. That's why there's no voltage. Because all my voltage is used by the load when I have a single load in a series circuit. So that's why. So the only 2 times I got voltage is what? When I'm going on either side of my load. Which also means we've just proved that between here and here are electrically the same, right? So in theory, I should be able to test it either here or test it here. Just like we've proved that this is electrically the same as this because there's no volts being used in any of these. So again, I could test it here or here and see if I got voltage. So now let's put 2 loads in with an open switch.
Mm-mm. 0.
0. Yeah, no current flow, no current flow. Doesn't matter how much resistance we got. 0 volts. How about this one?
0.
0.
Okay, how about this guy?
0.
0.
How about this one?
0.
0.
0.
How about this one?
12.
12.
12, right? Because it's on either side of my switch. So I got 12 volts here and ground here. That's 12 volts. How about number 6?
0.
0.
0. And number 7?
0.
0.
Okay, let's close the switch. Now what do we have on number 1?
Oh no.
12.
1 is 12.
6.
6.
1 is
6,
12.
right? Because it can't be 12 because if this was 12, this guy wouldn't have any. And we know that I have one path of current flow and they have to divide the voltage. So I take my 6 plus my 6 is 12. 12 divided by 12 is 1. Then I take my 1 times my resistance. 1 amp times 6 ohms is the 6 volts. You're correct.
Oh,
So what's number 2?
4.
4. Number 3.
100.
10.
10.
Yeah. I made the math tough for you guys, didn't I?
Hmm.
How about number 4?
6.
6.
6.
Number 5?
0.
0,
0.
Oh, 0 here.
Number 6?
12,
12.
12.
12.
How about number 7?
12,
12.
12. Okay, now we looked at what happened when we had unwanted resistance.
8.
8, you're right.
This is
How
4.
about number 2?
4.
4.
4. 6.
So slow down a little bit here. Now, how much resistance do I have? 4 plus 4 plus 8 is how many ohms?
16.
16,
16. What's 12 divided by 16?
1.5.
Yep, 0.75. So what is 4 times 0.75? Or
3.
what's 3/4 of 4?
3.
3. How about number 3? What do we have?
Uh,
8.
3.
I'm not sure how we're getting 8 here. That's way off. I've not heard the correct answer yet.
Don't understand either.
Well,
Travis.
how much resistance do I have? 4 plus 4 plus 4 is how much?
12. You
Oh,
get
12.
4 is
12
answer.
divided by 12
4.
is how many amps?
3.
1.
1. 1 times 4 is
4.
4.
4.
Oh, so it is 4. Okay. But, okay, never mind.
We sure?
Yeah.
Okay. I mean, this is hard when I'm not in front of a whiteboard with you guys in the classroom. That's why I wanted to go over these again. So this bottom one, what's my voltmeter going to read for number 4?
Six.
No, it's about 4 points. About 4.
There's no decimals.
18.
Well, no, we can have decimals.
18.
Oh, okay.
Well, how many
14
ohms of resistance do I have total?
14 divided by 12 is about, I don't know, 0.8. With
No, it'd be 16 divided by 12. 12 divided by 16, wouldn't it?
Which is 0.75.
okay, it's 3.
0.75.
It's 3. It's gonna be 0.5. 3.
0.75 times 6.
Right, which would be you're absolutely right. 0.75 times 6.
4.5.
4.5.
Stupid.
So everyone see how we got there? You guys seem to struggle with these last ones.
Yan mute mo.
I got confused at 2, but I remember now.
Okay. So it's a good thing I went over it a little bit then.
Yeah.
Okay. Awesome. Okay. Now we finished off last time looking at our blower motor circuit. And I said for us to highlight through the low. And so we start at power, come through the switch, come through our first resistor, our second resistor, our third resistor, all the way to our blower motor to ground. So my question is, how many volts do I have here? What's my voltage here? At the right here.
12.
12 or system voltage, right? I mean, because I don't think, I would have taken either answer in this case. The most correct answer is system voltage because we use system voltage a lot on a car because that changes whether the car is running or not. So if I'm key on, engine off, system voltage might be 12.4 volts. If the car is running, system voltage might be 14 volts. So you're going to hear the term system voltage used a lot. So as we move out of the academic of solving for the unknown where we use 12 volts because the math works, And we get in the real world, a lot of times instead of 12 volts, we use system voltage because we're going to find out very quickly that batteries don't have 12 volts in them, even though we call them a 12-volt battery. So I have system voltage here. And as we use system voltage, if I have system voltage here, how much voltage should I have here at C?
Where?
At C, right here on the blower motor resistor assembly, right here. How much voltage should I have here? If I have
12.
system voltage here, how much should I have here?
12.
System voltage.
Same thing, 12 volt system voltage, right? Because there's no load. This is just a switch. So if I go to A, should I have less voltage?
You have a resistance.
Yes.
Yeah, because I went through a resistor, correct?
Yes.
And then if I come down to D, I'm going to have even less voltage because I've gone through 2 resistors.
Yeah.
And E, I have even less voltage, correct?
Yes, because
Correct.
Okay. So now, how much voltage do I have at B?
0.
0. Okay. Anybody else?
Well, I mean, system voltage.
System voltage. Okay, so I got 2 extremes here. Let's see who's correct. So I've got this, because obviously my switch is not connected here, so I have no power going out this way. But if I come down through here, this is connected, isn't it? So I would have voltage come back through here, all the way to right here. So this would all have system voltage because I can't drop any voltage across that resistor. It's an open circuit. This is why people get confused when they're testing electrical things. Because if I'm on low, I'd have system voltage on B and it'd go less and less and less. I go to M1, now I got system voltage at 2 places. If I go M2, I'd have system voltage at 3 places. Wait a minute, what's going on here? I don't understand. Well, it's because I have all these open legs that just have potential. I'm not doing anything with the voltage, but it's still there. So that really confuses people when it comes to how things work. Why is my meter, or why is my testing device giving me the reading it's giving me? We can see here, here's where the path should be. But wait a minute, I know we all agreed I'm gonna have less voltage here, and even less voltage here. We couldn't agree on what I'd have on the back part of the circuit. And this is really important because if low doesn't work, but M1 does, and I have system voltage here, doesn't it tell me this resistor isn't open? So maybe it's a switch problem and not a resistor problem? Because think about it, my resistor is pretty easy to get to. This is part of my HVAC control assembly that's mounted on my dash. I got to take my dash apart and take this thing out to get to the back side to test it. But this is real easy to test. So I could go here to low. Do I get any voltage? Oh man, I don't get any voltage there. It looks like a bad switch. I could then go to M1 and go, oh, wait a minute, I got voltage here. That means the resistor is good. So I could actually figure out I've either got a broken wire or a bad control assembly by not even testing it at the control assembly. And at that point, I know the next step is what? Take the control assembly out. Well, some of these control assemblies might be 2 hours to take out. I only got a half hour to check the blower motor. I'm done. I need to what? Write up what I found. The reason why the blower motor is not working is there's no power going to blower motor resistor assembly in the low setting. That's why low doesn't work. My recommendation is pull the HVAC module out and test it, look for a broken wire, verify it's a bad module. One of the things that gets us in trouble, and I see this a lot at school, and school is different because it's your car or it's what we're doing. We're not going back and forth with the customer. But the problem is these habits get carried off into industry, is that the customer asks a specific question. In this case, why doesn't my blower motor work on low? Well, the reason why it doesn't work on low is, hey, there's no power coming here. That's the answer. Why is there no power coming there? That's a different question. Okay. So that half-hour answer of the why doesn't my blower motor work on low is different than the 2-hour question of do we need a new control assembly? So you see kind of we can break this down hypothetically. We also talked about on high speed, I don't even go through the blower motor resistor. And someone had their car last week, and I apologize for not remembering who, they said, oh, my car does that. I think I need a blower motor resistor. Who was that? No takers. I know I wasn't
I think
drinking.
it was Mac.
Oh, it was Gary.
Oh,
So did you get a blower motor resistor this weekend?
Nope. Definitely did not.
I was just curious if you fixed it or not. Okay.
No, not this weekend.
Mr. Grant,
Yeah.
okay, you have B, C, and A. So if you would put that switch on V, it would got resistance on A, B, C, and A, and D.
Right. If I turn the switch to low and fed power through this way, we would have system voltage here, a little less here, even less here, even less here, and a whole lot less here. We would drop it as we go. And that's the importance of knowing what to expect at different test points. And that's why it's really, if I have a car that doesn't work right, the first thing I do is get the wiring schematic. Because I can't go test the vehicle without having the schematic. Unless it's a circuit that I've repaired several times and I already have it memorized. But that's the first thing I need to get. And the thing that's funny is everyone wants to go test the car. No one wants to go and look up the information to test the car. And then they wonder why they spend 3 hours chasing their tail. And
Hey,
the
bro,
car's
quick
more-
question. Quick
Yeah,
question
George.
about the resistor. So
Uh,
the resistor is there. So each of the component, it works off a different current, right? So the resistor is to drop that current so that component could read that voltage, so that could work.
Right.
Is that
Yeah, exactly. As long as we're flowing current through that leg of the circuit. I can only draw voltage through the resistor with current flow. So it has to be, so in other words, if I turn it on here to M1, I drop voltage here, and drop voltage here, but B, I would not drop any voltage because it's not a complete circuit. If I turn the dial to M2, I'd have system voltage at A, I'd drop the voltage to D, drop the voltage to E, but I'd have full system voltage at C and B because they're open parallel legs that don't have any current flow.
I'm a little confused, sir.
Okay. Not
So
surprised.
if they don't connect it, how can they have 12 volts?
Because they're connected to the circuit on this side, but they're open on this side. So they're connected here, right? So if I feed power in here, power is going to feed back all the way to here, and it's going to feed back all the way through here. It just can't complete a circuit. If I can't complete a circuit, I can't drop voltage because I'm not flowing current. Did that help, Gabriel?
Fine.
Yeah, because we're still connected here, but I'm connected before we drop voltage. And therefore, since there's no current flow through these resistors, we can't drop any voltage through them. If I'm feeding the power in right here at position M2. And I apologize. Normally I have printouts of this and we spend a lot of time highlighting and kind of talking about it. But again, I just kind of want to get us thinking about, you know, when I get a voltage reading on a meter or a scope or whatever I'm using or a power probe, is this the voltage I should have here? Don't think automatically something's wrong. I need to look at the schematic, and that's where using the highlighters is really helpful for kind of tracing through and seeing. So let's look at another schematic here. So this one has 3 relays in it and 2 fan motors. And this is actually a series circuit and a parallel circuit depending on what we're doing with the relays. So When I run it in series, each of my fans gets basically half the voltage. And when I run it in parallel, they each get full voltage. So on low speed fan, they're both on. On high speed fan, I can turn one or the other or both on. So you can see where I might have a car that overheats or the high speed fan comes on a lot. The customer might complain about the noise because one of the fans is broken or one of the wires is broken. So now only one fan works, which means you have no low speed. So if we look here and you can see, remember I said these are drawn in their default position. So here's an open switch. This switch is normally here. And then here's another open switch. So if I energize this switch, I command this on, now I have current that comes through this fan, up, over, through here, down through here, through this fan, over to ground. That's low speed. So all I gotta do is turn on one relay and power is gonna come from here, through the first load, through here, through the second load, and down to ground. Each fan's going to get about 6 volts. But now say I turn this, I keep this one on, but now I turn this one on. So now instead of going this way, we're going to go this way. What happened? Did I go straight to ground now? So now I have 12 volts to that fan. How if I turn on this relay? Now what? I've just turned this relay on. I got power, ground. I got 12 volts to this fan. So I can run both fans on low speed, this fan on high speed, or both fans on high speed. Oops. Or this fan and this fan on high speed. This is GM. This is pretty typical of how a lot of manufacturers do this. Toyota makes it a little harder. They use 4 relays. But this is why you have 3 fan relays for 2 fans on a General Motors vehicle. Because I'm getting low speed and I'm getting high speed. And I'm getting single control on the high speed. So this is where cars will overheat or run too hot, maybe because one of the relays goes bad. Or one of the fans goes bad. I can no longer make a low speed circuit. So now I'm either overheating or not overheating. I no longer can control it down at a normal operating temperature. And the computer turns the relays on.
Does it have anything to do with when the fan turns on, but way too late?
This would not, because that's controlled by temperature sensor. So
these are the fans for the radiator.
Right. Well, on this system, the temperature sensor goes to the computer, and the temperature sensor is actually on the engine, mounted right by the thermostat on the engine side of the thermostat. So that way it's not dependent on the thermostat to open, and it measures the engine temperature and it turns the fans on based on the engine temperature. And that's how most modern automobiles work. We haven't used fan switches in the radiators really since the 90s. So if they're coming on late, that's a temperature sensor issue. If they're not coming on at all, it could be a wiring, a fan, or relay issue. Or I guess it could still be a temp sensor problem. But that's why to diagnose this vehicle, I'd use a scan tool before I ever use my DVOM. Because my scan tool, I can talk to the computer. I can see the temperature that the computer thinks it is to see if it's turning the relays on. I can use the scan tool to turn the relays on and see if the fans work, which means I don't need to wait for the car to get really, really hot before I go try to check to see if I have 12 volts or 6 volts or anything at my fan. I can do it on a cold engine and just use the scan tool to turn it on. So once we start controlling things by a computer, the next question we need to ask is, can I use the scan tool to control it? So if I'm working on an older car that doesn't have a computer, my first tool is going to be maybe a power probe or a DVOM. If I'm working on a modern car with a computer, my first tool is probably going to be a scan tool so I can talk to the computer. So depending on the year of the vehicle, I'm going to choose different tools. So here is a starter circuit. And there's actually 3 circuits here. So if you look, here is my starter motor right here. I'll give you guys a second to look to see what it takes to turn this guy on.
Yeah. Oh, shit. Do you have my cheese in? My cheese?
Today's been a speak during school. Sorry, for you, that's good.
So, like I said, let's look at this for a minute and I'll walk through the process. Like, here's the starter motor that we're trying to get to go roundy around so we can start the car. And there's actually 3 circuits on this page it takes to make this thing come on.
Who can throw it? Okay? Why?
So I like to start at power because I think power is one of the easiest places to kind of start it. You got to start somewhere. You can start at ground. But I'm going to start at power. I got a battery right here. And this dashed line means that's a junction. So this, and this are all connected. So I got battery power coming over to here and I got an open switch. Okay. So this switch is open and I see it's controlled here by a coil that pulls it in. This happens to be a solenoid. It's drawn very similar to a relay. So, okay, so we got to do that to pull this in. Okay. So if I look here, this goes up and this goes across and feeds power to here and here. So I could come over to here and look, okay, I got power here and it goes to an open switch. That's my second open switch. So now let me go across the top some more and come down to here. I got a fuse. Oh, here's a switch. And what is this? This is what? My neutral safety switch or park neutral switch, isn't it? Or no, it's the ignition switch. I'm sorry. So I got to turn the key in the ignition switch to start, don't I? So if I turn it to start, okay, that explains. Okay, so start. Now I got power coming through here and I got power coming through here. And this just tells me it goes off somewhere else. It's not part of the operation of this circuit. I come down here to what? Now I've got what? My neutral safety switch or my park neutral position switch. So I have to be in what? Park or neutral for this to get power. So I'm in park so I can get power through here. Now I come up and, oh, good, I can energize the relay. But what else do I need? I need power and I need more than just power, don't I? What do I need? I need positive and
Ground.
ground. So the ground has to what? Go to the other side of the relay. I come over here and, oh, there's a switch in here and it says what? It's part of the PCM. So the powertrain control module controls the ground. So not only do I have to turn the ignition switch and I have to be in park, the computer has to say it's okay for me to start the car. So this is like the chip that you have in a key for the immobilizer, right? The computer's looking for a chip and a key, things like that. Maybe the car's overheated. It's too hot to start. I'm not going to let you start it. So there's several reasons why the computer might not let you start the car, but say the computer lets me start it. So now I've just energized this. Now I got power going through the starter relay. Oh, and here's the load for that circuit, comes over to here. And what? That just activates the solenoid on the starter. So now I can close the contact here, which allows power to go through. And we're finally starting the car. So is my car going to start if any one of these 3 circuits has a problem?
No.
No. I need all 3 of these to work right before this car is going to crank over. So when someone says, hey, I think I need a starter because I turned the key and nothing happens, is that a guess or do you think they know what's wrong?
I guess.
It's a guess, isn't it? I mean, look at all this stuff. I mean, I could have a bad battery connection. I could have a bad battery. I could have a bad connection in this wire at the starter. I could have a bad starter and solenoid. Oh, I could have a bad starter relay. I could have a blown fuse here. I could have what? A PCM that doesn't want me to start the car because it doesn't like my key today. I could have a park neutral position switch that's bad or out of adjustment. Again, a whole bunch of more electrical connections. I could have an ignition switch that's bad and not sending power out. Again, more electrical connections. Or I could have a blown fuse here. That's a whole lot of things that could keep me from starting my car and going home, isn't it? Wouldn't this be a hard car to fix if I didn't take the time to go get the schematic so I can figure out how it works and then I can decide where I want to test stuff at? I mean, I could test right here, and boy, if I get power here and this doesn't work, I know this is bad. But if I don't get power here when we're cranking the key, then is it the relay? Is it the other? How easy is it to get to the starter? Some starters are pretty easy to get to. Some are under the intake manifold. It's 5 hours to get to it. I'm probably not going to go test it at the starter, am I? I can't. My customer's not going to pay me 5 hours to take it apart just because I want to go see if it's bad. So then maybe the relay looks like a good place to test, because at the relay, I can see what? Is the computer grounding it? Am I getting a signal from my neutral safety switch or my ignition switch? Am I getting positive here, negative here? Do I have positive here? And am I sending positive down? I can, remember I said relays are great central places to test everything and figure out what direction I need to go. Plus, they're usually easy to get to. Plus, could I apply power here at pin 87? And should it make the starter crank over?
Yeah.
If I put power here, that should energize this, cause this switch to close, and the motor should turn, right?
Yeah.
So again, I can test from here by supplying power. I can see if I got power and ground coming in. Relays are great places to test things at. It's one of my favorite places to test stuff at. They're easy to get to usually, and it allows me to split all 4 parts of the circuit to see where the problem is. Beats the heck out of what? Going underneath the car to look at the transmission, take apart the steering column to look at an ignition switch. How about check the relay? And many systems that use relays are like this, where that's the best place to start diagnosing it. Because if I go to the relay first and I don't have any power right here coming down, doesn't that tell me to go check the fuse? But if I check the fuse first, then what? I'm going to check this fuse next, and then I got to go to the next thing. But if I go to the relay, it's central. I can kind of figure out where I need to go. So, how many of you knew it took so much to start a car?
I knew about the starter, but that's it.
Yeah, a lot of people are familiar with either a clutch safety switch or a park neutral switch. They've all experienced not being able to start your car because you don't have it in park or something. I think a lot of people kind of don't necessarily think about that, but when they're asked, they really do know that. But this is a pretty typical starting system. This is Ford. This isn't even anything high-end. So this is, you know, again, every car is slightly different. But it's all about, let's get the blueprints. Let's see how they built it, then I can figure out how I want to test it. So I'm going to show you next probably the hardest type of schematic we see on a car. And no, I won't have any test questions on it. Power windows. Power windows are probably the most complicated schematic on the car. Why? Because on a DC motor, if this is power and this is ground, it goes one way. If this is power and this is ground, it goes the other way. So on a motor that I want to go up and down the window, I need to apply power and ground and then switch them. Power and ground, power and ground, power and ground. I need to switch them whether I want to go up and down, which means I don't have one switch, but I need 2 switches. I need to switch the ground to power and the power to ground. I need to do it both at the same time. So which makes the schematics really confusing. Let me tell you, when you remember it's just a DC motor, I need power and ground one way and power and ground the other way, it makes a little more sense. But these, I've had experienced, really experienced diagnostic techs get turned around on windows. We had one at the shop several years ago. My boss was working on it. Before he bought the shop, he'd been there 16 years. He was the top diagnostic tech. And he was working with one of the other technicians, and they'd already put 2 window switches in it from the dealer, and it would work from here, but not work from here, and it's blowing a fuse, and what the heck's going on? They couldn't make heads or tails of the schematic. Long story short, they came and got me. I looked at it, figured out the switches they were getting from the dealer were made wrong. I cut something that they forgot to cut on the switch to isolate the circuit and fix the problem. And it took me probably 5 minutes to figure that out. They'd been on it all day. But these are really confusing. It's not that I'm that brilliant and they're that dumb. It's that these are that confusing. So if we look here, I've got a window motor right here. I have a relay, another relay. And what I have here, if you notice, I've got some letters that are coming down to other items. And let me bring this a little bit bigger so I can actually read it. So we've got A, B, C, and D. Everyone see the A, B, and the C and D here? So what? A and B right here are both what? Power, aren't they? If I look at C and D as they come off here, this comes off a motor here, and this is coming off a relay here. So I don't have any ground here. All I have is power. I'm going to go to the other half of the schematic, and now what do I have? I have ground. So if I have ground comes across here, and we can see where everything else comes in, I have A coming in here, I got B coming in here, and I have C and D. If you look at these switches, ground comes over, and I have ground here, we have ground here, I have ground coming across, and I have power in the middle. So if we look at what happens here, because right now everything's off. So as I move this switch and the whole thing moves together, I make one side power and one side ground. If I go the other way, then I make the other side power, other side ground. So I'm switching it, and that's what allows this to move. But you see where it gets complicated, because I have a master switch, but I also have the switch on the door, and they both have to do the same thing. So everything from the master switch passes through the door switch. So if the door switch is bad, the master switch normally won't work either. But I can have a bad master switch and still have a good door switch and be able to work it. But you see why it's confusing, because you can imagine when this shifts back and forth, now we're putting power on one and ground on the other. If I swing this the other way, now I'm putting power here and ground here. So I'm switching this back and forth, this shoe, on a slide inside the switch so that I can reverse that. So a lot of times what happens when these go bad, either I get bad contacts for the power or the ground. So that's why a lot of times when a switch goes bad, the window will go down but not up, or it'll go up but not down. Think about it. If it goes one way and not the other, it probably isn't the motor, because the motor doesn't care which way it's going. So therefore it goes up but not down, typical switch problem. Down but not up, typical switch problem. It can't be a motor. It goes down. Got to be a switch. Does that help? You see the logic I use there? So based on what the customer tells me, a little bit of understanding of the system, based on the customer's complaint, I can figure out, did we mechanically break a regulator? Do I have a regulator? I'm going to get all kinds of noise, or you're going to hear it bind up because the regulator broke. Or it's just not attached to the window at all and it's just down now. I heard some noise. The window fell in the door. I'm thinking that's a regulator problem. I'm thinking that's a mechanical problem. But if it's an electrical problem, if the window goes one direction and not the other, the motor's fine. It has to be a switch. Is that helpful? You see the logic I employed there? A lot of the things we fix are just by stepping back one or two steps and thinking about it. Instead of jumping in, I need to rip this off. I need to see what's going on. Let me get the panel off. Let me look and see what's going on there. Oh, I need to get both panels off because I got a switch on the driver's side and a switch on the passenger side. I need to rip everything apart because this isn't working. Oh, step back. Let's think a little bit here. Let's get the schematic. Let's look at the symptoms. Let's think our way through this and figure out what we actually have to take apart. So is it helpful kind of going through some of these schematics?
It is. I still need a lot though.
Yeah, you do, and it takes a while, and I'm introducing you guys to some complicated schematics, and I'm not going to test you on any of them right now, but I kind of want to give you guys an idea of what we're going to see instead of just the oversimplified, here's a straight line, and then you get a real schematic. It's like, where do I start? And as we get into engine management systems and we get into other things, you're going to see different schematics, and I want to be able to explain them to you. And I want to be able to discuss them with you. And that's a big reason why I put them in here so early in the class. It's not to intimidate anyone. It's just they're not as complicated as they look. Once we start applying some of the things we've learned, we can figure our way through them. So here's a little case study that I'm going to use some wiring schematics to fix. Yeah, let me pull back up the chat. So crazy exterior lighting observations. With the brakes applied, the brake lights work okay, but the front park lamps and license plate lights come on. The odometer and clock get dim every time I put my foot on the brakes. When I turn the right turn signals on, the left park lamps also come on, and the license plate lights are also flashing. The odometer and the clock get dim every time the lights outside flash. If I turn the hazard lights on, all the hazard lights work normally, but my license plate lights also flash, and so do the lights on the dash. My left turn signals work normally. My headlamps, when I turn on the headlights, all the brake lights come on, but my headlights and parking lamps seem to work normally. So here's our wiring schematic. And what we do here is I've got 4 wiring schematics, and I highlighted in red where the current flows in each of these positions. And what we want to look at is what they have in common. Because obviously what's going on is we have circuits that are what? Shorted together. We have stuff going, because my license plate lights aren't supposed to flash with my turn signals, right? So I got to look for some place that everything shares. So here for my brake lights, we got a power, and it comes down from the top. Here's my third brake light. Comes over here through my combo switch's default position, and it comes down to my 2 rear brake lights. Now, if I go to my right turn signal, I use a different fuse through a different switch. Now I've actually had to move the switch from my combination switch, and it comes down and it lights up my instrument cluster and both of my right side lights, my front light and my rear light. If I turn on my hazards, now we're lighting up what? Both my rear and my front lights. Different position on the combination switch. Now, if I turn on my headlights, I don't go through the combination switch at all. I go through a whole different fuse, through my headlight switch, and I come down here and we're going to light up my rear lights here for my license plate, as well as both my rear lights and my front lights. So what's the one component that we used in all of these? What's the one place we had power go through every time?
Down at the bottom.
Down at the bottom. Okay, what down at the bottom here? This? This? Which one down at the bottom do we go through every time?
Go through all of them again?
Okay.
The second one to the right.
Second one to the right. So
Yep.
that means the only place that these circuits could be shorted is right here. Isn't that correct? So I either got the wires melted, the socket melted, or a bad bulb. What happened is the bulb burned out. It has two filaments in it. One of them burned and went over, it melted to the other one. So all that crazy operation is because of a bad bulb. But we figured out that that's where the problem has to be by looking at the schematic, tracing out each function and realizing there's only one place we can be shorted.
That was cool.
So there is a real world example, even though it was a simple repair. I still have people ask all the time, you know, if I have you do the repair, are you going to charge me for the diagnosis? Well, what's harder here, putting the bulb in or knowing that the bulb's the problem? Right? I guarantee, I'm sure every one of you could put a bulb in. Not every one of you would have been able to figure out that that's the problem this quickly before this class. And again, you didn't go to school to learn how to necessarily put the bulb in. You learned going to school to learn out why we put the bulb in, right?
Right.
So I like using case studies. I use them in a couple of different of the chapters I use. When I do advanced testing, I do a lot of case studies because it's cars we've actually fixed. So other circuit testing tools. I got a little bit here about some testing tools. So this is a power probe. This is the newest one. This is the 4 is the picture here. But what's kind of cool about it is it has a wire that hangs off the side, which is ground. So I can actually put ground here and put power here and light the light bulb up to test it. Well, if I can light a light bulb up, I could probably use it on a window motor or a seat motor or anything else. And it has a circuit breaker in here for 10 amps. Load substitution tools is like you see me talk about a cycling circuit breaker or a homemade load substitution box. If we have a vehicle that's blowing fuses because of a short, we'll use a load substitution tool instead of the fuse. That way we can hook up that load substitution tool like a light bulb, and then when we fix the short, the light bulb goes out. So that way you don't keep plugging in fuses and why is it blowing? We just redesign the circuit. We're blowing a fuse because we're going from power to ground without a load, and we know we have to have a load. So if I take the fuse out that's blowing and put a load in there like a light bulb, as soon as I make the light bulb go out, I just fix the car. And here's the homemade load substitution box I was talking about. This has 6 bulbs in it, so it makes 15 amps a draw. And there's how it's wired up. And here's how we'd use it in a circuit. So here we have a short before the load. So as soon as you put in the fuse and turn the car on, the fuse blows. Well, that's going to be kind of hard to fix, isn't it? I keep blowing the fuse. If I use a resetting circuit breaker, then I make it hot and melt the wires or cause more damage. Or, you know, the circuit, I'm going to wear out a circuit breaker. They're not cheap. If I just keep putting fuses in every time I disconnect something, that's going to get tiresome. So what I do instead is I'm going to take the fuse out. I'm going to put that load substitution box in. And when all these lights are nice and bright, I have a short before the load. As soon as I fix this short, my lights go out or get real dim. What's easier? You trying to figure out why a fuse is blowing or trying to figure out how to make lights stop working? I think it's easier to get lights to stop working. Because you think about it now, could I wiggle the wires or wiggle stuff, and if the light flickers, I know I'm getting close to the problem?
Yeah.
So it's great for intermittence, right? The fuse blows and it doesn't blow it out, but it blows again as soon as I start driving the car, or it blows every. Well, maybe I need to put something else in there or do a load substitution or something that I can see exactly when it's short so I can diagnose it on an intermittent. Here are some other tools, sensor simulator tools. We actually use these to put a wiring, so I can tell if the wiring's shorted. We do this a lot with networks or things like that, where I'm looking for computer communication and computers can't talk. So I'll put a signal on the network. If I can put a signal and no one talks, that means I have a break in the network, so I can use it to find where the break in the network is. If I can't put a signal on, that means it's shorted. So I use those for diagnosis or replacing sensors sometimes on cars. There's some other circuit finders for finding opens and shorts and wiring. Again, just different tools. Back probing tools for back probing wires, which we'll get into when I talk about sensors. Some front probing tools. These are tools that are calibrated for the exact size of the connector, so we can plug connectors together and make harnesses or test them or look for loose connections. These ones right here are the lower part. This is what I was talking about, that you take a fuse out, plug this in, you can put your amp meter around this loop. And you see there's still a place for a fuse here. So you put that way I can measure amperage. That's what makes the fuse box such an easy place to test, is having a tool like that. And this tool right here, we're actually checking to see if the pin is damaged. What happens is if people use the wrong test equipment, they push something in and it opens the pin up. Then they plug it back in and it no longer makes a good connection. So the circuit won't work. So what we do is we use tools for drag testing, which is what you see them there, where you actually slide it in and it should have enough tension to hold the connector in midair. If it doesn't, the connector is opened up. It's got a problem. And we actually have that problem on one of the trainers in the classroom. I have someone who's making a lot of background noise.
That's probably me, Brian. I'm at work. Sorry.
Okay. Okay. Yep, it was you, Miguel. Thank you. And so the drag checking tools. Let's see. These are for relay testing. You heard me talk about testing at relays. And I'll try to do a video demoing these before the end of this class. Not today, but before the end of our session. These are great because what you do is you take the relay out, you plug this in, and then you plug the relay on top of it. And these little things right here are for all the pins of the relay, and they're labeled. And you can see I have a lot of different relay designs. There's 8 of them. And so that way I can test everything from underneath the hood right at the relay. Just take the relay out, plug this in, put the relay on top. I'm ready for testing.
Yes, I got it. Thanks.
So again, how can it's a lot, because a lot of times the bottom of the relay box is really hard to get to, but that's where I want to test it at. And I really want to test it with the relay in place. So they make tools for that. But no, I did do several videos this weekend, so we're working on getting those edited and done. And different kinds of test leads. Here's kind of a pre-made universal test harness where it allows me, has males and females here, and the meter goes in here. We have male to male and female to female adapters, sometimes for adapting leads. These are inline fuse jumper harnesses, retractable shroud sometimes on some leads. So these are called a banana plug lead. There's 2 main kinds of leads we use on scopes in automotive. One is a banana plug, which is what we see there. It's a 4mm banana. The other one we have is called a BNC, and that is shielded. It goes on and it twists, so it's looks more like a single wire, even though it's 2. Goes to a coaxial cable, and it has little ears on one. You slide the ears over and twist it to lock it. Those are the 2 types of scope leads that we use in auto. Almost all of our equipment we use at ECC uses the banana leads. And banana leads are banana leads. It doesn't matter so much where you get them. You just want to make sure they have good insulation so you can get a clean signal. And I also put this in here. This is just a chart. Shows based on the number of feet and how many amps at 12 volt, what the minimum wire size you would need to run that size run. So if you're going to put in fans, lights, anything else, this gives you a minimum wire size. So that's just a reference for you. I'm not going to test you on it. So was this helpful going through this today? Okay. Let me stop our share here for a second. I'm going to change PowerPoints.
Brian, I actually got a relay right here. I took it apart just to look at it,
Right?
just to see how it works in here.
Yeah. And you can see you got a field coil in there.
Yeah.
And you got a set of
Relay.
contacts. Yep. Yeah, standard Bosch relay.
That's why it failed, because the little switch here is constantly working, right?
Yeah. Yeah, so
Clicking in there.
you flow current through where the windings are and it pulls the switch closed.
Yeah. Maybe so the student, they could get a relay, they could just look at it, see how it works.
Yeah, and I've got some pictures coming up, and I have a nice animation, a 2D animation I built on the relay. But no, relays are definitely cool, and they're such a great test point. And they fail a lot. So I mean, you know.
They're constantly clicking in here.
Yeah, exactly.
When you
Every
power
time
it
it's energized, it clicks.
Yeah. So that's another way to test it, right? If you don't click.
Yeah, but well, you got to be careful because some of the new ones are solid state. They don't click anymore.
Oh, okay. See, I'm still stuck with the old school.
Yeah, and the old schools were great because I should be able to tell you could put your hand on it even in a noisy shop and feel it click.
Mm-hmm.
But some of the new ones are solid state. They don't click anymore. And that's where those testers also really come in. But you can see that if you hold it up, you got a 5-prong relay there or 4?
Yeah.
5-prong, right? Yep. So then you plug that right into the top of one of the testers I showed you. Then you have all the little ears, one for each of those pins, and they're all numbered. The same numbers on the bottom of the relay. The 30, the 87, the 85, 86,
87,
and 87A.
You can actually use it to power, boost up ground and boost up power too, right? The relay?
Yeah, you can use a relay to control power or ground.
Yeah.
Just depends on how you wire it in. Usually they're wired on the power side of the circuit, but not always. I can also control them by switching power or ground. So you can control them either ways. Relays are really neat devices.
I'm still trying to understand them.
Yeah, we'll get there. Okay, so I'm going to start this next section using a PowerPoint I have, although I do like some of the stuff with the CDX PowerPoint, so I'll probably work on reconciling those a little bit today. But I want to start talking about some battery technology. So, got to give us some guidelines and kind of start looking at batteries. There's always a lot of curiosity on batteries. There's also a lot of misinformation on batteries. So this is a great chance to talk about both those things. So the battery is the heart of the system. Therefore, other components can test bad if the battery is not performing properly. The battery is only used to supply power during times when the engine isn't running or when it's starting. However, if the battery is bad, it can cause the voltage regulator in the charging system not to function properly and not to properly control alternator output. So in other words, if my battery's bad or if my battery's weak, I can't test my starter because in order to test my starter, I have to have a good supply of voltage. On the other hand, my charging system, which runs my car as soon as I start it, if my battery's bad, my charging system won't work right because my charging system responds to what the battery wants. In other words, if the battery's bad and doesn't want a charge, my charging system will not charge it. If my battery's bad and wants too much of a charge or it's shorted, it'll actually overheat my charging system and damage it. So if my battery's not good, I need to take care of that first before I can test my starter or my charging system. If I rush through and go, yeah, I know it's not good, but I really think I just have a bad fill in the blank alternator or starter, they have a high likelihood of testing bad with a battery that's not functioning properly, but yet when you replace them, you still haven't solved the problem. So again, so when we're testing the car, and this is really hard with customers because they tend to be impatient. You know, their car doesn't start, they're in a hurry. When you tell them, look, you know, I need to charge the battery for a couple hours and then we'll see what we got. They don't want to wait a couple hours. Well, you know, the only other choice is I sell you a new battery. Well, don't you have a new battery you can put in for testing? Well, we don't have loaner batteries. My customer doesn't want to buy a new battery that I've used for testing for the last 2 months. I wouldn't want to buy that battery, right? If you're buying a new battery, you're buying a new battery. So customers a lot of times are not very patient when it comes to that. And this is a point where as technicians, we need to be patient. I see so many bad decisions made because people are put into a situation where they're in a hurry. So my 12-volt battery, first rating we look at is CCA, cold cranking amps. So my cold cranking amps is the current that a battery can deliver for 30 seconds at 0 degrees while maintaining voltage of 7.2 volts at the battery. So that's how we rated batteries forever, cold cranking amps. And it's nice because it gives us something we can kind of compare one battery to another with. So, but it's not only the cold cranking amps that make up a battery, but also its reserve capacity. And we see this a lot on European vehicles. What the reserve capacity is it's the ability of a car to sit there with electrical loads on the battery for an extended period of time. So I may have plenty of juice to start the car, but if you leave me for 2 weeks, I'm dead because I don't have enough reserve capacity. European vehicles need a lot of reserve capacity because that's one reason why the batteries in a European vehicle tend to be huge. It's still a 12-volt battery, even though it's twice the size or 3 times the size of the one in the Honda. One of the differences is they want a lot of reserve capacity. And the most common thing we see this in is either as RC reserve capacity, which is one rating system. The other is as amp hours, an amp hour rating. So simply put, it's the number of hours that a battery will last with a 1 amp drain and still stay above 0 volts. Well, wait a minute. I can't use my battery all the way down to 0 volts, so I probably can't use it that many hours, right? I mean, I need a certain amount of voltage to start my car. So if the draw on the battery is 2 amps, it'll last half as long and so on. That is why a battery with a lot of CCA may not be sufficient for a particular vehicle if the amp hour rating is too low. And we see this a lot when people put lower amp hour batteries, cheaper batteries, but they have the CCA into a luxury vehicle. Right? Why do I need to buy that expensive battery? This one will fit. See, it starts the car. I knew I was right, but gee, if you let the car sit for 4 days, it's dead. So then what? They think they need an alternator. So they're going to go back to the same XYZ auto parts and buy an alternator because they got the wrong battery. And guess what? That's not going to fix the problem. So then they think they have a drain on the car they're not supposed to have. So they're looking for that. All because they cheaped out and put the wrong battery in. So here is a battery right here, a battery rating. This happens to be a group size 58. Has 540 cold cranking amps, 675 cranking amps. So back in the 80s, before then, auto parts stores sold to auto shops. And if you went into an auto parts store, you were probably paying full list and you didn't get a discount. And in the 1970s, companies like Dorman and some of these other companies came out where they now had auto parts stores really designed to the public. And we see those today in O'Reilly's, AutoZone, that type of stuff. So Kragen, those type of auto parts stores. So, and they no longer sold things at list. What they did is they sold things at a discounted price. 30% off list, for example, or 20% off list. So a better deal than people were getting at Napa or these other stores that were really geared towards the industry. Well, one of the things that happened is they also came out with this new cranking amp rating, because customers were just looking for the number. Hey, I need a 700 Kohler cranking amp battery. Well, here's a 700 cranking amp battery. We just left a word off, and look at how much cheaper it is. So it was not uncommon back then for customers to buy a battery over the counter based on cranking amps, not on Kohler cranking amps, which is what the manufacturer specifies, and it was not adequate for the vehicle. Today, many battery manufacturers give you both ratings. And here we can see I have an RC, or reserve capacity, of 80 amp hours. So the MT in this case stands for Megatron. That's the brand sales recognition of the battery. The 58 is for the group size. So with a 58 group size, whether I buy it from Interstate, which is what this one is, or whether I buy it at a Die Hard, or whether I buy it AC Delco, or I buy it off of XYZ Auto Parts, if it's a group 58 battery, that means it's a certain height, a certain width, a certain length, and it's molded in such a way that the hold down will fit and everything else that's designed for that group 58 battery. So we have several group sizes of batteries, and every car has a group size that's specified for it. So you're supposed to have the correct battery for that particular vehicle based on its group size and what it's required to have. That group size also comes in for a certain amount of cranking amps. Now, in that group size, I can normally buy a good, better, or best battery. I would be able to buy one that doesn't meet the minimum standards. So, but that is one of the things we'll look at. The other thing that will change between the good, better, best is how much reserve capacity I have. So the difference between a $50 battery and a $100 battery is more than just what you're paying for it. It really, got it. It really comes down to what's the, what are the other features? What's the reserve capacity? How many amps does it have? Also, a cheaper battery tends to be a lighter battery because it has less material in it. That's why it has less capacity. For me, I buy the best battery I can get because I don't like walking. So, and the reality is a battery is going to last me 5 or 6 years. So if I buy a $60 battery at 5 years, that's $1 a month. If I buy batteries twice as much, it's $2 a month. Well, is it worth an extra $1 a month to not walk and not have problems? For me, it is. Do I like putting out the $120 when I buy the battery? No, I hate it. It's the last thing I want to do. But by the same token, my last battery I pulled out after more than 5 years, it was still working fine. It was just over 5 years old. And again, I don't like walking. If it only costs me $2 a month, why risk how many more months is it going to last? 4 months, 6 months? So for $12, am I going to risk being stuck somewhere and walking? Heck no, put a new battery in it. Because I want reliability is what I want. I want to be able to get in my car and have it start. Here's another issue we have with batteries. As the temperature drops, we lose battery capacity. So at 80 degrees, I have 100% of my battery's power. At 32 degrees, I only have 65% of its power. At 0 degrees, I only have 40% of its power. If I'm at 20 below, I only have 18% of its power. So as it gets cooler, I lose battery capacity. So that's one reason why manufacturers specify such a high cold cranking amps. Do I need that on an 80-degree day? No. Do I need it on a 32-degree day? Probably. Do I need it on a 0-degree day? Definitely. Do I need it when it's 20 below? Absolutely. Do they know where that car is going to be sold? Do they know where you're going to go driving? No. So in Southern California, we're spoiled. We can drive around with a bad battery for 6-8 months and still have a car start. Because What was the temperature this morning? Right? I mean, we're normally in the 60s and 70s here. You know, we get a cold spell, what, in December? I'm here to tell you that first cold spell, we sell out of every battery we have in the shop. All those customers, we were telling them you should get your battery replaced. My car starts fine. It's not a problem. They're on the phone yelling at us the first time it gets cold. My car didn't start, and it was just there for an oil change. Yeah, look at your paperwork. We told you you needed a battery. The other days that batteries go bad is extreme heat. So when we get a heat wave, it's over 100 out, batteries start not working. The other issue we have is the amount of energy it takes to start my engine increases as it gets colder. So at 80 degrees, we'll call that 100% as a starting point. So at 32 degrees, now I need more than 1.5 times the energy to crank that engine over. So I've only got 65% of my power, but I need 155% of the energy. You see where this is becoming exponentially a problem? Now I'm at 0 degrees. I've only got 40% of my battery's powered, but it takes over twice the energy to crank the engine over and get it started. At 20 below, I've only got 18% of my battery's power, but it takes 268% of the energy to what? Crank it over. 2.5 times as much energy to get it to start with less than 20% of my available power because my battery's so cold. So you can see where that really comes into play. Now, let's think about these numbers. This is using the right oil. What if someone uses the wrong oil in their car and they put an oil in that's thicker than it's supposed to be? Would that make this problem worse?
Yeah.
Absolutely. So isn't it interesting how something as simple as using a different weight oil, using a 530 instead of a 020, is going to affect how much energy it takes to start the car. That's going to have effect on my battery. Because it has an effect on my battery, and my battery is drained more when I start the car, that means my charging system is going to have to work harder to put power back into my battery. It also means that what? My starter is working harder to turn the engine, so it's going to need more amps. That means the starter's getting hotter. The starter's going to last less time. So you see where everything we do on a car affects other things. Kind of crazy, huh? So 12 volt and hybrid technology. Conventional vehicles use a 12 volt lead acid battery. Hybrid vehicles use a nickel metal hydride or lithium ion battery, normally producing between 100 and 300 volts. The HV battery has 50 kilowatts of potentially deadly energy. That's a bunch. Good technicians fully understand both 12 volt and high voltage batteries. So my question is, as the temperature goes down, what is the effect on the battery's power?
Goes down.
It goes down, doesn't it? So as the temperature goes down, the battery's available power goes down. So 12 volt battery principles, and the CDX does this a little bit differently. Some of the stuff the CDX has I like better, but I had some things in here I wanted to make sure I caught. So that's why I'm starting off with this one. So electrochemical device that produces and stores electricity. All batteries produce direct current or DC. So the reason why we use DC on a car is I cannot store AC energy. I can only store it in DC. So even if it's my house and I have a solar panel on my house, and if I want to, I have to make that energy in DC, convert it to AC so I can turn on the lights and the TV. But if I want to store that energy, I have to convert it back to DC. Then if I want to use it off of my battery, because you hear the Tesla power walls, I mean, they're advertising like crazy, all that. That's a DC battery. That's the only kind of battery we can have. So we're converting that AC into DC, and then from DC back to AC. Every time we convert, we lose a little bit of power because it takes energy to convert. But that's why it's in DC, and that's true for all vehicles. So it changes chemical energy into electrical energy, current and electrons flowing out of the cells. So I do not go too far into the chemical energy, chemical process. And the reason is I just don't care that much. You know, if a battery's good, it's good. If it's bad, it's bad. Watching little electron fish go back and forth and all that really doesn't help me determine whether it's good or bad. And I know the book spends some time on this, and that's fine. I want you to have that understanding. That's part of the class. I'm just letting you know, I'm not going to concentrate on you because understanding doesn't always equate into fixing a car. We're going to concentrate more on the car side of it. But I don't want to lose anybody either. So during the charging, battery converts chemical energy electrical energy back into chemical energy, current flowing back into the cells from the charging system. Energy is stored for extended periods of time. So we use a chemical reaction with the lead acid to store and release DC power. So battery cycling, the time between discharging and charging battery cells. So this is important. Excuse me a second here. Grab a water. Because different batteries have different rates. So for example, some batteries are made to be slightly discharged and then filled back up, slightly discharged and filled back up. Other batteries are made to be drained almost completely and filled back up. If I do a full drain in a full recharge with a battery that's not designed to do that, I'll destroy the battery doing that just a couple times, maybe even just once. On the other hand, if I have a battery that's designed to be cycled down all the way and charged back up, if all I'm doing is using what's on the surface, it's going to cause the battery to go bad. It's going to lose its capacity to what's called deep cycle. So that's why we have deep cycle batteries and automotive batteries. That's why we don't put a deep cycle battery for our engine battery, because my deep cycle battery is designed to slowly bleed off a small amount of energy. My underhood battery is designed to give you a whole bunch of energy, a couple hundred amps all at once, and then get it back in a hurry, but never go down very far. So battery design really varies, and we want to make sure we use a battery that's designed for the application. Deep cycling, going from a very low charge to a very full charge. If I'm using 6-volt batteries, they're designed to be a deep cycle battery today. They do still have some automotive 6-volt batteries, but few and far between. Most of what we see now are deep cycles. If I'm deep cycling a regular automotive battery, it will kill it. It'll shorten the life of the battery. Matter of fact, doing it once, if I have a battery and it goes completely down to 0 or 1 volt on a car battery, if I do that once, I have just damaged that battery. It's never going to be 100% again. If I let that happen on my motorcycle, that battery's done. It's never going to hold a charge right and work right again. Because a motorcycle battery is a lot smaller. It's still 12 volts, but much smaller. So a load, as we've discussed, is any current using device connected to a simple battery cell. Current will flow through the load. So that's a circuit, right? A load conductors power. So inside a battery cell, I have a negative plate and a positive plate. We have a container that we put those plates in, which makes up the cell, and electrolyte. And the book does do a great job in the CDX of going through and showing some animations and showing this stuff. So that is good. We do need to understand kind of what's going on inside there. That's also why some batteries weigh a lot more. It's because of how they make the plates. How many plates did they put in there? The electrolyte is our liquid sulfuric acid. That should stay inside the battery and never come out. Batteries for automobiles are sold what's called wet. That's where they already have the electrolyte in the battery when you buy it. If I buy a motorcycle battery or some other special use batteries, they come what's called dry. That's where the battery acid is in a powder, and I would mix that with distilled water and actually set the battery up and balance it using a hydrometer. We really don't do that in the field anymore. Hazardous waste is part of it. If I buy a motorcycle battery from Interstate, even though they store them dry, they're going to fill it up, charge it, set it, balance it before it ever comes out to me. So we don't have electrolyte in the shop the way we used to. The exceptions to that would be if I'm doing marine stuff, boats, because they have large DC grids for their power. So they'll run the generator to charge the batteries, and the batteries will supply all the 110 and everything on the ship. So they use electrolyte there to where they keep constantly rebalance the batteries. If I'm doing golf carts or forklifts where they run 36 battery volt setups, I may be rebalancing them. Or if I'm running off-grid solar, where I'm running multiple batteries, I need to balance the battery array. So I will be manually going through and using a tool called a hydrometer and adding acid and adjusting that. But for cars, we just don't do that anymore. So there's 3 types of batteries that we use on an automobile. One is a lead acid battery. That's the most common. And then we have an AGM, absorbent glass mat flat, which is used by Mercedes, BMW, and some other manufacturers. And then we have the AGM spiral, which we see as an aftermarket absorbent glass mat battery. Now, these batteries are not interchangeable. The charging systems and the computer systems are very different between what I need to run an AGM battery than what I need to run a lead acid battery. So here is a standard lead acid battery. We can see on the top here, I have 2 caps. And so if I pop these caps off, I would see 6 cells. Each cell generates 2.1 volts for a total of 12.6 volts. So my 12 volt battery is really not a 12 volt battery. It's a 12.6 volt battery. The reason why they've been 12 volt batteries up to this point is I didn't want anyone doing decibels any more than necessary. So that's why I made them 12 volt batteries on all of our exercises. In reality, they're 12.6 volt batteries, 2.1 volts per cell, 6 cells in series. Therefore, I have a 12.6 volt battery. So if I hook things in series, for example, I have AA batteries here. Each of these batteries is 1.5 volts. So if I take my positive to negative, I'm now wired in series. I now just made a 3 volt battery. If I put another one, it'd be 4.5 and so on. Has anyone ever opened up a 9 volt battery and looked inside? There is 6 cells inside here. Each cell has 1.5 volts, the same 1.5 volts I have in my AA battery. Same chemical configuration. Less capacity, more voltage, because they're what? Smaller. So, right, what's the difference between this big D cell and this little AA? They're both 1.5 volts. The difference is what? The capacity, the amperage. Here I have 9 volts, 6 very small 1.5 volt batteries. So say I wanted to build a bigger battery. Could I make an 18 volt battery by taking 2 9 volts and clicking them together? And now I have an 18 volt battery? Could I plug another one in and make a, I don't know, a 27 volt battery? Can I do this a bunch of times and make a pretty strong battery?
Yeah.
Again, not a lot of amps. I now have a 36 volt battery. Is that kind of cool? Everyone following me on that?
Yeah, that's cool.
So I still don't have a lot of amperage because all my cells are small, but I have 36 volts. I'm probably not going to be putting this on my tongue. You know, when you're a kid, your mom said, well, just check the 9 volts. They're going to tongue. If it tickles, that means that it's still good, right? Or was I the one dumb enough to do that? I see people shaking their head. Yep, I was the only dumb one. Okay.
Yeah, I probably would have been, yeah.
So, but I'm not going to do that with 36 volts. I have a feeling that's not going to feel so good. And so when we make our battery for the car, we're doing the same thing. We're taking 6 of these 2.1 volts batteries, putting them in series to get 12.6 volts. That is our typical lead acid. This right here is an AGM flat battery. If you notice, it looks very similar to my other one. No serviceable vents on top. It's sealed. Now, just because a battery's sealed doesn't mean it's AGM. But this one does tell me it's an AGM battery. And these batteries do not like to be discharged below even 11 volts. These are very sensitive to voltage. So a lead acid battery on a normal car, when I crank the car, my voltage can go down as low as 9.6 volts. And when I start the car, it can go up as high as 15 volts. So we're talking 5.5 volt range between when I'm cranking the car and when I'm charging it back up on a normal lead acid battery. My AGM batteries don't like to go below 11 volts cranking and really don't like to go above 13 volts charging. A 2 volt range. So you can imagine if I take this AGM and throw it in a car that's not designed for an AGM battery, the charging system's not going to control it right. It's going to cook this battery and it's not going to last as it should. So this is an AGM flat. This is what the original equipment manufacturers use. We also have special charging precautions for AGM batteries and special chargers for AGM batteries. I can't use a regular battery charger on them. Now this right here is an Optima battery. These are an aftermarket AGM battery, and these are a spiral cell battery. And they have the same limitations of the factory AGM battery. They don't like big voltage ranges. And they need to really have their charging system control. That's why these don't hold up in vehicles real well. So you think, why do people use them? Well, first of all, my regular lead acid battery has water or liquid electrolyte in it. So if it falls over or splashes, acid goes everywhere. This, I can mount it on its side. It doesn't leak and it still works. I can put a lot of power in here. So these have some applications that they work excellent in. But the car you're driving every day that you want to have the battery last for 5 years is not one of them. And unfortunately, if you go into XYZ Auto Parts store, this is the battery they try to sell you because it's the best. And then you keep replacing it every 1 or 2 years and you don't understand why. Square peg, round hole. Great technology, but again, charging precautions. I can't use any battery charger on it. I need to use an AGM charger. My car thinks it has a lead acid battery. It's going to try to charge this like a lead acid battery. It's going to cook it. It's going to overheat it. It's going to destroy it. Here is a deep cycle battery. Now on the deep cycle battery, we have slightly different posts where I have the regular post, but I also have a threaded stud over here to attach wires and stuff to. So I can attach it differently. So kind of a good overview on our batteries so far as for what we're doing. And we're going to get in tomorrow into more on batteries and into actually how we test batteries. I do have a battery test video and worksheet up, so I'll work on getting module 3 up because I know some people are moving right along.